Okay, they couldn't afford the whole dish because of budget cuts. Yeah? No, I'm just kidding. I don't know. This is one way to do it. You can make a radio telescope this way, right? You don't have to have the whole parabola. You can make a visible light telescope this way as well. Okay? But they just make them, they make the whole thing, right? Okay? And the story here is funny. This is a funny story, kind of. Okay? These guys discovered the cosmic microwave background. They discovered the radiation left over from the Big Bang by mistake. Yes? In fact, they thought it was noise and they were trying to get rid of it. Does this sound like a familiar story? They thought it was noise and they were trying to get rid of it, right? And they try and they try and they try, and sure enough, it's coming from out there. And everywhere they point this telescope, they get this noise. And it's where they detect it is about 7.35. That's the wavelength, right? Okay. And by the way, down the hall from Penzias and Wilson was a team of scientists that had booked time on this telescope. Like 2 weeks later, I believe it was. 2 weeks later, they were going to look for the cosmic microwave background radiation. Yes? These guys are going, what is this noise? Where is this coming from? They're like, oh crap. It's the Big Bang. You've discovered the Big Bang. They get the Nobel Prize. The people didn't get the Nobel Prize, right? It's like, that's sort of sad, right? Okay. So it's coming from out there. Here is the measurements of the black body curve. This is the theoretical curve, right? These are measurements, and they are way off, and that's because we're looking at it through our atmosphere. Yes? Our atmosphere is not neutral to infrared, is it? Yeah? It's not neutral to wavelengths of radiation like that. We know this because that's like the greenhouse effect, et cetera, right? Okay? And so basically trying to look at the Big Bang through the universe is like trying to look through a blanket or something like that, right? It's just very, very difficult. So really to do this careful measurement, don't you have to spend billions or millions of taxpayers' dollars and put something above the atmosphere to do this? Yes, so we did that because this is important stuff, right? We sent the COBE, I forget what it stands for. Maybe it's on the, if I hit the right arrow, right? Cosmic Background Explorer, COBE, right? They send it up there, and basically this is all heat shielding to shield it from the Earth, which is also another warm object, right? These are solar panels to power it, and then it's going to point away from the Earth. It just basically points itself away from Earth with gyroscopes. I believe it probably had like liquid helium or nitrogen or something cooling it down. I know that the next one did, right? And basically they measure that temperature. Gamow predicted that the black body curve should be about 5 kelvins, right? They get about 3, about 2.726. That's pretty good, huh? Right? But here's the cool thing, right? This is a theoretical prediction. These lines, that line there is what it should be. If you take a poker, stick it in a fire, heat it up and pull it out, it glows red hot, yes? That's called black body radiation. This is the theoretical curve. We've got this. This is a very, very good theory. This is the birth of quantum mechanics. We've got exactly, we can predict exactly what wavelength it does, right? What wavelength it does. And this should, I think this is temperature, okay? And so, or intensity. This is intensity here. This is wavelength, right? And we've got a really good prediction. These little squares are the actual data points, yeah? That's pretty good fit, isn't that pretty good? But the story's better than that, okay? They actually exaggerated the size of these error bars. Those are actually little error bars, right? They exaggerated that so you could actually see the line through the bars, right? It's actually, the error is much smaller than that, right? So now you can have any theory you want about the creation of the universe, but it's got to put the radiation created by a hot object everywhere in the sky. Yeah? And it's got to have the right wavelength, as if it were stretched over the right period of time that we know it's been stretched, right? But if your theory does that, then, you know, there you go, right? So this is, you know, this is huge evidence for the Big Bang, right? Okay. Okay, so 1992, the other thing that they did was they looked at little fluctuations. It should be all the same everywhere, but it's not quite. Okay, did you guys ever learn something called the Heisenberg Uncertainty Principle? Yes, no? Okay, it's that you cannot simultaneously measure the position and momentum of an object. It has to do with quantum mechanics. This does not sound familiar? No? Some student, I think Patrice came up with this joke. I don't know, you'll appreciate it, right? It says the Heisenberg Uncertainty Principle states that you cannot simultaneously determine an object's position and its momentum at the same time, right? So the policeman pulls over an electron, and he says, do you have any idea how fast you're going? And the electron says, no, but I did know my position exactly. Okay, so the reason why this doesn't affect baseballs, I mean, it does affect baseballs. Baseballs are governed by the Heisenberg Uncertainty Principle, but the random fluctuations from what you would predict are minuscule. So a baseball would change its speed by a fraction of an atomic diameter per second or something like that. But it's not like it's going to speed up and then you're going to miss. Okay? So, but for small objects like electrons, the Heisenberg uncertainty principle rules. Tiny objects are just crazy that way. Okay? And so what they did with this thing was they said, gee, another prediction of the Big Bang was that the universe was small. Yes? Yeah, it was a singularity. Isn't that small? That's like as small as it gets, right? So if it is small, it should have been governed by the Heisenberg uncertainty principle. Therefore, it shouldn't be homogeneous exactly. It should have little fluctuations, and we should be able to see them. And they should be exactly what we predicted with the Heisenberg uncertainty principle. Yes? Did they find that? Yeah, they did. Right? Okay. And I actually met this guy. Right? These are the fluctuations here. Right? And these are just tiny, tiny fluctuations. Right? And I actually met the guy. I don't have the thing there, right? But some guy named Smoot said that seeing this fluctuations was like looking into the eye of God, okay, which is a little bit hyperbolic, a little bit of hyperbole there. I think it's actually like looking at quantum fluctuations on a very small object, but you know, there we have it. Okay, now this is especially appropriate because we're going to do the extravaganza tonight. We're going to blow big bubbles, right? Have you ever taken a bubble and like blown on a bubble and had it like oscillate? Yeah? Yes, sir. Are you helping bring stuff over? Yeah, like right after class we're going to go off and load up the trucks, etc. Yeah? Okay. So you take a bubble. If you ever blow on a bubble, it sits there and oscillates, yes? Okay. Those are called spherical harmonics. The Earth, or the universe, was once something like a four-dimensional sphere that I can't quite picture. It should have oscillated because it emerged. It should have undulated like a balloon. And so we sent up a satellite called Boomerang that actually measured these undulations, and these are actually harmonics. This is one mode of harmonic. That's another mode of harmonic. This is like the first harmonic on a guitar, second harmonic on a guitar, kind of a stuff, right? Okay. So now you can have any theory you want about the creation of the universe, but it's got to place a warm object across the sky, the radiation of that, right? It's got to predict that the universe was once small, right? And it's also got to predict that in 4 dimensions it undulated like a balloon, right? So we have some really good evidence, right? Well, okay, the COBE probe was not accurate enough. So this is a more high resolution picture of this. And in 2003, 2006, these are the findings, right? The universe is 13.7 billion years old, not 10 or 15 billion years old. Both numbers had problems, right? Okay. It's composed of 4% normal matter. Let's just pause a little bit here. 22% dark matter, 74% dark energy. Yeah? This dark matter is not normal stuff. We don't even know what it is. Right? So this is a little bit embarrassing. 4% of the universe is the only part that we really know about, and the rest of it we don't really know. Okay? A little bit embarrassing. Right? And then the Hubble constant is about 70.1, not 50 or 100 as some researchers suggested. And is that it? Right? And that the universe is flat, and we'll talk about what flat means when we talk about the curvature. Right? But let's hit the right arrow. So take a look at this standard model here. I think you've got this in your notes, don't you? Okay. So let me just develop an idea here. What the Big Bang created was just pure energy, right? So we could talk about photons, particles of light, right? If I've got a photon with enough energy, it can actually, there's something weird that photons can do. It's called pair production. Okay? And this sounds very exotic, but it's happening right now in the cabinet behind Matthew back there. Okay? Don't worry about it. Okay? But there are some radioactive rocks. They're not very radioactive. Don't worry about it. Right? Okay? And they are creating, well, actually one of the things it's doing is it's creating positrons. Okay? Now a positron is just like an electron. Okay? Only it's positively charged. A positron is just like an electron, only it's positively charged. Now, if you had enough energy to do this, this energy of this photon, right, can turn into matter. Electrons are matter. A photon, a particle of light, is energy. This happens all the time. In fact, at CERN, where they're doing all these particle collider experiments, they don't really give a crap about what they're using. I think they're using protons, colliding protons. They just want that energy. They've got the kinetic energy, and with that energy they can create matter. Right? And they can create these particles that haven't existed since the Big Bang. Right? So telescopes are time machines. Particle accelerators are also things that create super, super high energy